All right, my name is Allison Bamberger, and I am the program director here at the Masonry Institute of St. Louis. Thank you all for being here on a very rare Monday for a seminar. Thank you all for reading the description. I said, yes, it's definitely a Monday, it's not a Wednesday. We are very happy that you're here for a topic that is very germane to what we all experienced on Friday. So I hope we're going to get a lot out of it. So today we are going to talk about structural design for tornado loads on buildings. I think we can all see, if we just look about a mile that way, we can all see exactly why that's important. We are giving AIA credit for this course. You can see our learning objectives here. They're also on those handouts right in front of you. And I will be passing around the gift card box for our giveaway. We've got another wonderful Masonry Basics guide, very handy for all of your masonry design needs. We also want to thank John J. Smith Masonry Company for sponsoring this today. They're a wonderful partner of ours here, and I know they do a lot with architects and engineers all over the region, so we thank them for their continued support of the Masonry Institute of St. Louis. Here today we've got Greg Bryant from our Structural Coalition in the back. He probably helped you sign in if you needed it today. Thank you, Greg. We've got Bruce Augustine, he's our technical director. Pam Hallway is up in front. She is, she keeps the lights on. She keeps the turbines turning. And Dave Gillick, our executive director, is not here today, but we thank him for everything that he does for us as well. Next week, it will be our final seminar of the season. Saying it so, I know, but we'll start up again in September, so don't worry. But you don't want to miss Seamless Transitions, Perfecting Material Changes in Masonry Design, Michael Schuler. If you've got any questions about that, if you need to register, didn't get the email, stop by my office. I can certainly help you out. But it's the last one of the year, so we're going to blow it out. It's going to be a great time. Definitely hope to see you next Wednesday. Today we are so excited to have Dr. Marc Levitan here to speak with you all. He is the lead of the National Windstorm Impact Reduction Program Research and Development at the NIST. He also is the recipient of the Samuel J. Hayman Service to America Medal for his work on developing standards to make structures tornado resistant. So, not a better person that we could have here today to talk to you all about what we all just experienced and will probably experience again soon. Thank you so much, Dr. Levitan.
Thank you so much, Allison, and I'm glad to be here. And regarding the date, that was an accommodation when I got invited to come here. It turns out I was already here for the 15th America's Conference on Wind Engineering, which starts this afternoon and runs all day through Thursday down at the Convention Center. If you're interested in that, talk to me afterwards or just Google 15 ACWE. There's a whole week worth of wind loads, and I'm going to give a 3-hour version of this course later on this afternoon, what I'm going to give you all right now. And I just would like to say, and thank you for the gracious introduction, Allison, the Samuel J. the SAMI Award, the Samuel J. Service to America Medal, was to myself, my colleague Long Fan, and the whole tornado load wind team. And we'll talk about that a little bit today here. One of the members of that wind team, Alex Griffin's here in the room, one of your locals. He's part of our Tornado Task Committee from ASCE 7 that wrote this. And I see some other so familiar faces. I spent a fair bit of time here in your state after the 2011 tornado and down in Joplin. Very instructive, which really, as we'll see, kind of led to a lot of where we're at and some of the things that are happening here today. Okay, so we start out and let's look a little bit back into the situation of where we got to where we are today. But first of all, we haven't typically considered tornadoes in conventional engineering design. And from what I understand here, you guys, at least in St. Louis, are still on the 2018 IBC. So I would strongly encourage you to work with your building officials, your city council, county council, whatever that is, regarding, hey, now's the perfect time before we start on this rebuilding to upgrade to the 2024 IBC, get the tornado load requirements and a lot of other great advances that's in there. But we haven't typically considered engineering design for tornadoes in conventional design. And by conventional, I'm talking about just our regular construction, not nuclear, those sorts of things. And there's this whole series of common misperceptions that tornadoes are too rare, that the losses from tornadoes are small compared to other hazards, There's nothing we could do about them. We have inadequate knowledge. We'd all have to live underground or in concrete bunkers. It'd be too expensive. And the perceptions may be shaped by the few violent tornadoes per year that make the headlines. I'll also say that NIST may perhaps play a role in those perceptions. Before it was called the National Institute of Standards and Technology, it was the national, founded 100 and change years ago, 120 some odd years ago, as the National Bureau of Standards. And in a 1959 wind report on wind pressures for the United States, they had a brief couple of paragraphs about tornadoes. I've highlighted a section here. The wind pressures and suctions in the immediate path of tornadoes are considered to be so great that construction strong enough to withstand them is not economically feasible. Therefore, in recommending design wind pressures for building codes, do not take into consideration the violent forces expected within the narrow path of a tornado. So that was sort of what was understood before. So a tornado, there's nothing we can do about it. Actually, it turns out that perhaps they didn't have as good of overview and to be able to see all the stuff that we can see with the internet now. There was an early engineering analysis from a tornado in St. Louis 130 years ago that was very devastating, with 255 fatalities and over 12,000 buildings damaged or destroyed. And a report that was published by ASCE in their transactions, and part of the discussions for that report says it's scarcely possible that buildings would yield to any of the pressures found by Mr. Bayer in writing this report, and the degree of provision of structural capacity would neither be difficult or extravagant to resist those tornadoes. Now, they were looking at kind of multi-story buildings right here, and we'll find out the same way. Really, once you get to above 3 or 4 stories, the structural loads, we're not going to see collapses of those. We're going to lose cladding and things like that. But by the time you have a robust enough structure that's already going to be several stories tall, you've got the bones there that you need to be able to resist a tornado. So how rare are tornadoes? The first thing we look at this chart goes back to 1950 with our official records. And we see, oh my gosh, what's that, climate change or something, right? We've got a few tornadoes in the early years, and later on, no. We didn't start out recording those tornadoes. The early years of the database were built through looking at newspaper records and other kind of local records, et cetera. So we didn't have that, and we didn't start recording tornadoes really as a scientific field of study until much later in the time. And then even only when we get to the early 90s did we start to install the Doppler radar network across the U.S. And so once we get past the early 90s, we can see that the number of tornadoes, actually let me put the laser pointer on here. The number of tornadoes, there's a lot of year-to-year variability, but the number of tornadoes is relatively constant on average, something like 1,250. Now that's the number of reported tornadoes per year, right? A large number of tornadoes go unreported, because where do you get reports from? The radars themselves typically don't catch the tornado. They might catch a rotation that indicates a possible tornado if it's close enough and on the ground, but unless the tornado happens to go right over the radar station or within a couple miles, it's not measuring any wind speeds or anything. But so we have a possible indication, et cetera, and until you go out and you verify from the damage that you see, then that's how a tornado gets reported. Well, okay, you've got plenty of population density right here, but go an hour west or east or other places, whatever. In most places in the central United States, the population density in terms of buildings, there's less than 10 buildings per square mile. It's pretty hard to hit a building with a garden variety tornado that might be an EF1, that might be 20, 30, 50 yards wide and a mile or two long. If you've only got 10 buildings per square mile, it's hard to hit a building like that. A lot of the smaller and weaker tornadoes just get missed. Okay. Where did tornadoes occur? Tornadoes occur in all 50 states. They actually occur I don't know that there's been any recorded in Antarctica. Of course, there's not much population down there to see them. But there are others. We have tornadoes in all the continents. We have tornadoes in all 50 states. But the overwhelming majority occur east of the Rockies, right? We'll also note a few things here, as you might not think, wait a minute, there don't get many tornadoes on the East Coast. Sure we do. I'm in Maryland. We had one about a half mile from my house, an EF1 in June last year. We've had EF4s in Maryland and other intense ones. We see more of the darker colors with the more intense tornadoes are in the central U.S. over to the southeast, but we see some of these darker dots even over here in the east. We see a lot along the coast. Hurricanes can spawn sometimes dozens or 50, a couple of dozen tornadoes might be spawned off an individual hurricane, usually on the advancing right front quadrant, sometimes a state or two ahead of the hurricane. Okay. If we think more about local impacts here, as part of some work that we were doing earlier, we went back from as mining a lot of different records in the last 30 or so years. These are just the schools that we know about that have been verified that were hit by tornadoes. And so when you think about adopting your codes, and I don't know if you have requirements here with the 2018 IBC, did you keep in the requirements for tornado shelters in schools? Does that anybody know? Do you require tornado shelter, ICC 500 tornado shelters in schools? Nobody's raising their hand. I guess perhaps you might be one of the communities that amended that out, right? Some communities have amended out the storm shelter requirements. We put some of this work together to help communities understand what their risk is, and maybe you should think about when you adopt the later one, not doing that. Some schools, we have one over here in Oric, a school was hit twice, and one over here in Gillespie, I can't quite read that here. A couple of schools have been hit twice. How rare are tornadoes? A couple of the same schools just in these two states got hit twice in the last 30 years by tornadoes. Tornadoes are not really rare at all. How many lives are lost in tornadoes? Tornadoes kill more people per year in the U.S. than hurricanes and earthquakes combined. Tornado fatalities are a buildings problem. 85% of all tornado fatalities occur inside of buildings. We can design for Mother Nature's worst. Storm shelters provide life safety protection. FEMA uses the term safe room. They're nearly identical. Their FEMA safe room requirements are nearly identical to ICC 500 storm shelters. In the center part of the country, like here, we're designing for 250 mile per hour winds, impact of a 15-pound 2x4 traveling at 100 miles per hour. There have been no reported failures of ICC 500 storm shelters or FEMA safe rooms. This gets investigated. When there's a storm, FEMA has a whole huge database of all the shelters they've funded. They overlay that. They'll take a look if there's any reports in the media that there have been storm shelters or safe rooms that have been hit. So typically someone from our community will go out and investigate. And we're proud to say that there's been a large number of residential safe rooms that have been hit by even EF4s and 5s, and none of those have been significantly damaged with no injuries. And there's been a smaller number now of even community safe rooms and shelters. How much damage do tornadoes cause? According to the Insurance Information Institute, catastrophe losses, so that's losses from events with over $25 million in covered losses. Events including tornadoes account for 40%. Hurricanes and tropical storms account for 38%. Wow, really? It's not a perfect statistic. The way they keep their statistic, hail gets mixed in here. So a lot of this is going to be hail and some other windstorms, but tornadoes is a big chunk of this percentage right here. So anyway, it's just certain to think about tornadoes cause huge percentage of our insured. The other thing that happens is a lot of the smaller tornadoes just aren't going to reach the level of 25 million for that because it only hit 5 buildings or 8 buildings, 20 buildings or something like that. And so a bunch of the tornado stuff would not be caught in here because a lot of the smaller events, whereas a hurricane or tropical storm, if it makes landfall, even as a modest one, it's going to be over 25 million, and so it's going to be all included. So there's a few different warts with this data, but that's the data that's available. Isn't most of the damage caused by the big tornadoes? Let's take a minute here to look at this plot. It's a little bit busy. So first, let's look at the black line, and this is the total loss. This is the average loss per tornado in millions of dollars. For EF0, that's our weakest tornadoes, up to EF5, that's our strongest tornadoes. And this is on a log scale, if we notice here. So we can see it goes up almost by an order of magnitude with each increasing intensity of the tornado. And but if we look at the total losses across all of the EF0s, that's going to be in the red. We take all the EF1s in the database. Let's look at those. Take all the EF2s, except for the EF0s, which our wind speeds are down to 60 or 70. I mean, we're ripping gutters off, and we got trees falling and stuff like that. We shouldn't see major structural damage down usually at the EF0 level. But once we even start to get EF1, we start to pick up that damage. We see, wait a minute, how do the EF1s cause almost as much damage as 2s, 3s, and 4s? Well, that's because there's a couple of hundred of these guys, and there's less than one EF1, EF5 per year. We actually haven't had an EF5 in like a decade or so. That's what happens. Is yes, these are more intense. The intensity of damage is much greater, like the Joplin tornado, et cetera. But these are much, much, much less frequent. Okay. So here's our opportunity for tornado loss reduction. We don't have to design everything to withstand the most violent tornado. That's what people just think. Oh, you have to design for tornado. I got to design for the EF5. Well, why? We design for a Category 5 hurricane hitting New York City? No. We do design for Category 5 wind speeds in Miami, because that's more likely. The hurricanes go up the coast. We Hurricane Sandy, or Superstorm Sandy, we can get in New York, but they're just less frequent. So the idea we have to have, there was a big hurdle to overcome to realize we could do the same thing for a tornado. Let's design for the common tornado, the garden variety tornado, like we do everything else. And what turns out, there's a reliability basis. We have that. But violent tornadoes are uncommon. The vast majority of tornadoes are much smaller. We have EF0 and EF1, and here's the wind speeds associated with these. So EF0, 65 to 85, EF1, 86 to 110. I mean, 110 or so is around your design wind speeds around here, depending upon which risk category you are, 110, 115, 20. And so we can design it. It's not exactly equivalent. Tornadoes, for the same wind speed, tornadoes will create higher loads for a few reasons that we'll get into today. But these are things we design for all the time. Right? Like I said, gosh, in Florida, we design for 200 miles per hour. South Louisiana, we design for 200 miles per hour. There's certainly things that we can design for. So most tornadoes, 90% almost are EF1 is 0, even with EF2 or less, 135 or less, 97% of all tornadoes. And not just that. Even those other charts that I showed you with the damage, this is the plot from our analysis of what happened in the Joplin tornado. There's probably some smaller pockets of EF5 in here as well. But if we look at that, most of the winds and most of the swath of the whole tornado doesn't have the EF3, 4, or 5, even if it's an EF3, 4, or 5 tornado. Those are small pockets with the highest wind speed. Most of the swath is covered by EF0, 1, and 2 wind speeds. In this particular case, 72% of the whole track area that was impacted had EF0 through EF2 wind speed. So we can design for a lot of parts of the tornado. So we need a paradigm shift here, ignoring the tornado hazards and design of our built appropriate environment, not an appropriate response. So the genesis of the tornado loads I'm going to talk to you about today was our NIST technical investigation of the Joplin tornado in 2011. This was conducted under NIST's NCST authority, National Construction Safety Team. That was an authority given to NIST after the World Trade Center disaster, when it was like, oh, which agency has the authority to investigate this, right? The National Transportation Safety Board is called in if there's a plane crash or a train derailment, right? There was nothing similar, so the Congress created something similar, didn't give us any budget for it, but told us to go out and do that. So we've done and NIST has a long history of doing disaster and failure studies, but that was a new additional authority that they gave us. Our study of the Joplin tornado was our first really tornado study. It was the most comprehensive study of a single tornado really that's ever been done, including looking at the meteorology, the storm characteristics, the building performance, emergency communications, human behavior, fatalities, all 161 fatalities. We know where they occurred, what the people were doing when they happened, cadaver reports, all sorts of things like that. And understand all that, we developed a series of 16 recommendations, and a bunch of them for improving tornado hazard characterization, design and construction of buildings and shelters, emergency communications. When we conduct a technical investigation under NCST, we are on the hook to implement the recommendations. We have to write to Congress every single year, hey, what work did we do to get these recommendations implemented? So I'll say from a World Trade Center disaster, we finished our implementation of that last year with the publication through ASCE of a new standard for to prevent progressive collapse, disproportionate collapse. So some of these things, we might have to do a lot of R&D first, then we have to work with the standards and codes, communities, et cetera. So one of the things that we're really going to focus on today is we'll talk about development of tornado hazard maps, development of tornado design methodologies, and performance-based tornado-resistant design standards. One of the key things that we need to understand that's different about tornadoes than really just about every other hazard is the size of the building that you're dealing with is critically important to your risk. Okay? I don't care how many square feet the building is, I care about the plan aspect area, right? What's the plan? What's the footprint of the building? And to some extent to the shape. So tornado risk are a function of the building facility size and shape. Tornado strike probabilities increase with increasing plan area of the building or structure, or maybe we call it a target. What that also means is if you fix the return period, right, 50 years, 100 years, whatever years that you're looking at, 1,000 years, 10,000 years, for a fixed return period, the wind speed that you have to design for increases very significantly with the target size. And I think you can think about that. If I just said, God, the tornado right here that you just had, is it more likely to have hit any one little house, or is it more likely to hit a warehouse that has, 100,000 or half a million square feet? Of course, you said the tornado in some places apparently was almost a mile wide, but it's much more likely to hit a really big target than a small target. We talk about, so the development of our tornado hazard maps, so these are in our ASCE 7 standard. For risk category 3 is 1,700 years, and we'll see that's the same return period that we use for our straight line winds. If we have a small facility, 10,000 square foot plain area, we can see that our wind speeds or tornado speeds we have to design for are pretty modest, and they don't really cover that much of the country. If we go up to 1,000,000 square foot facility, now we're going to see, hey, we're going to go all the way up except for New England, and we're going to cover most everything except for the West Coast and the west of the Rockies. And we're going to have some pretty significant speeds, especially in the middle of the country. If we go up to a risk category 4, which we use 3,000 years, again, the same we use for straight line winds. Now we're seeing some significantly higher speeds that cover much more of the country. And then when we get to risk category 4, your tornado speed might even exceed your basic wind speed. We got about a 700-page report that documents in gory detail how all of these were developed. We have a series of 8 sizes that are mapped, and where it's from a point target of 1 square foot up, like I think about freestanding communications tower up to 4 million square feet. That largest size, we worked with the Nuclear Regulatory Commission. They were interested in facilities up to that size. As soon as we published the report, FERC, the Federal Energy Regulatory Commission, asked for a briefing, and we gave them some training, a couple of days worth of training on this, and they're like, do you have anything bigger? Our facilities are 40 million square feet for LNG facilities. So they can go up to that big, some of these big facilities on the coast and stuff. And so that's something that we're hoping to be able to produce larger maps. And we have short return periods all the way up to, again, the Nuclear Regulatory Commission was interested into very long return periods, 10 to the 6th, 10 to the 7th kind of things that they're interested in. One of the really important things, and this is a lot of the new research that we did, so all of the tornado load provisions are all based on a decade of research, really, most of which was a lot of it conducted by NIST, but a lot of it gleaned from the literature and other researchers and other collaborators. But the key thing is the tornadic winds are very different than straight line winds. We have a different climatology that we just kind of talked about with maps. They're very short duration. They have rapidly changing speeds and directions. They have strong updrafts right near the ground. They have a decreasing speed with height above the ground instead of increasing speed, so the profile is totally different. We have to worry about atmospheric pressure change, and we have much more intense windborne debris. So just as an example, we don't have time to go through all the research that we did, but for this one in particular, to look at the velocity profiles of the horizontal winds, we work closely with the mobile radar community, the Doppler on wheels, the real chasers, the science chasers, not the tourist chasers, right? And so they had, out of all the hundreds of records that they've had over the past few decades, they had a few dozen tornadoes where they had wind speeds near the ground, usually because of curvature of the earth, elevation beam angle requirements, distance away from the tornado, et cetera, like that. They're usually, even if they're measuring the tornado, they're going to be up 1,000 or thousands of feet up in the air. But there's very few records where they had data near the ground. And there's a ton of scatter here. This is like a normalized velocity profile versus height. So our normalized wind speed, we see there's a lot of scatter. But if we look at the median profile, gosh, it looks pretty uniform. And then actually increases a little bit near the ground here. That's what this dark line in the middle is, this median profile. And so that's what happens is the air rushes in, right? It's this vortex. The air rushes in along the ground surface, turns the corner in what they call the corner flow region, and then moves up. And so that get the highest wind speed, the horizontal wind speeds occur near the ground where the air is getting sucked in. Totally different from our boundary layer wind. Recently published a paper on that with some colleagues on the development of that in the ASCE Structures Journal. So for all of these different types of wind and characteristics of the wind, we had to make changes to our wind load design procedure. We have new probabilistic hazard maps. We talked about that. Made some changes to the gust effect factor. We don't understand that nearly as well as we should have. We made some changes to the directionality factor for the strong updrafts. The tornado simulator testing wasn't as good as it is now, and we had to do this work that was done in the 7 or 8 years ago now at this point. We used a boundary layer wind tunnel, but we tipped the back of the model of the boundary layer of the models into the floor of the wind tunnel to simulate an increased angle of attack and a net updraft on the roof right here to get to simulate an updraft on the roof and which enhances our roof uplift coefficient. Changes to our velocity pressure. We have atmospheric pressure change to worry about, and we have a more intense debris because of these updrafts, et cetera. We have much more intense debris environment that we have to work on compared to even say hurricane. And so just to really get a feel for this, we actually deployed last year for several different warehouse failures from this. And here there was a dash cam. This is in Lincoln, Nebraska. There's a dash cam from a car right here. We're looking at this side of the building right here. So we're looking to the northwest. Let me jump to the next slide. Play this for you. Sorry, we gotta skip the
thick absorbent layers. These napkins.
Okay, so we're going to see, we're over here, the tornado's going to come from left to right. Take a look at the trees right here. So we're going to see these trees over this time as it starts. The wind is coming. The wind is actually blowing towards the left, so it's blowing toward the tornado. That's the inflow, right? Moving towards the tornado as the air is getting sucked in. And we see over here, take a look at the roof over here. The roof starts to come off, then the walls are coming off. The walls are going down. We've lost that bracing that's provided by the roof for the structure, and in a matter of seconds, the building is gone. I'll go back and play part of that in slow-mo here. Let's change the setting. And really take a close look at what here. You know, this kind of construction, this tall wall, whether it's precast, whether it's reinforced masonry, etc., got some bar joists up on the roof, whatever, that connection, that roof is the only thing holding that wall up typically, right? There's not enough bracing laterally between the walls or foundation. They're not designed to be cantilevered, etc. As soon as that roof starts to come up a little bit, you lose that top of that wall. That wall's unstable now. Got to do a better job of designing that connection. And of course, not just the connection. Hey, you get a better connection there, then maybe you're gonna buckle the bottom cord of your truss or something like that. So you got to take that all the way through there. You can see this debris environment we got to worry about, right? Pretty nasty. So let's keep going. So I'm going to change hats now and put on my hat of the chair of the Tornado Task Committee and kind of walk you through some of the highlights of the ASCE 7 tornado loads. Prior to ASCE 722, we had a fair bit of commentary that we'd added in 2016 that said, hey, if you want to do something about tornadoes, here's at least a starting point. But everything that we have in 722 is all brand new and it's all science-based. Now, there's limitations to our knowledge, et cetera. We've tried to document that in the commentary where we had to use some committee judgment for something, but most everything else, we've got a lot of references in there of what we have. So the changes in 722, we've added some chapter 1, some tornado load requirement, mostly the risk categorization table. We just added the word tornado, so we use the same risk categories here. Just as a reminder, risk category 3, buildings and structures, the failure of which pose a substantial risk to human life. So that's going to be schools and nursing homes and jails, assembly centers, theaters, those sorts of things. Risk category 4 includes buildings and structures as essential facilities which need to remain operational, and buildings and structures required to maintain the functionality of risk category 4. So that's your physical plant for your hospital building, right? Hospital can't operate without its physical. We have made some changes to load combinations. We had very limited changes to wind loads, pretty much just to remove the limitation that says don't do tornado. We have a brand new chapter 32 on tornado loads, a brand new appendix with long return period hazard maps for tornado loads, particularly like for NRC and other users that are interested in much longer return periods. Reminder of our definition of essential facilities. These are buildings and structures that are intended to remain operational in the event of extreme environmental loading from flood, wind. We added tornado to that list. There's a bunch of other places in chapter 1 where they listed a bunch of hazards, and tornadoes is now included on that list. And a few other places in the presentation here I'm going to highlight. For essential facilities, we have some enhanced requirements for buildings to hopefully help maintain this functionality requirement. In our load combinations, we had W we used for wind load, we added W sub T for tornado load, determined in accordance with chapter 32. Tornado loads are not treated as a subset of wind, right? We got a chapter on flood loads, we got a chapter on tsunami. It's both water around the building, right? But they're very different. The nature of the hazards are different, those sorts of things. Right? So we treat tornado loads totally separate. However, when we go into the equations right here, in equation 4, the equations that deal with maximizing wind load, now we're going to substitute a W or a W sub T. So you have to calculate your tornado loads, you calculate your wind loads. When you go into the load combinations, then you see for each individual element that you're designing which one's controlled. If you remember, combinations 1 through 4 maximize our gravity loads, combination 5 maximizes uplift. So tornadoes are separate. Now notice here, on this equation 3, we have a live load or 0.5 wind. Why isn't it have a wind or tornado there? Well, because equation 3, we're maximizing something happening on the roof, right? Roof live or snow or rain. And this is our arbitrary point in time load. We don't have an arbitrary point in time tornado. I mean, it might be windy and there might be a little bit of wind blowing, so you might have a wind load, but you wouldn't have a W sub T there. Okay? And similar changes in the ASD combinations. Show those here for space of time. In chapter 26, we just added one sentence to the scope of the chapter. Risk category 3 and 4, buildings under structures, including main wind force and components and cladding, shall be designed and constructed to resist tornado loads per chapter 32. And we just point for the commentary, we point to chapter 32, and we've removed this whole section and half a dozen pages of commentary that we have on the tornado limitation. Our chapter 32, we look at our scope. It starts out with a flow chart. And particularly the seismic folks on ASCE 7 fussed at us about this. Oh my gosh, wind's already complicated. Really, the seismic people complain about wind load being complicated. Here you got to worry about that, both of those aspects. But they're saying, well, can't you give us some ideas when we don't have to do tornado loads? And so we came through and there's this flow chart. Tornado loads required. Well, if it's not risk category 3 and 4, nope, you don't have to do it. Are you in the tornado prone region? You're not in the tornado prone region. What we showed on the map is basically east of the Rockies. Nope, you don't have to design for tornadoes. Then we looked at, is your tornado speed greater than 60? You get your tornado speed from the map. If you're less than 60, you can stop right there. Tornado load won't control. In our regular design wind speeds, even for risk, at the lowest ends, any place here, they're 100, 110, whatever, by the time you get to risk category 3 and 4. And if the wind speed of the tornado is less than 60, just with our calculation procedures, it generally won't control anymore. Or if you have for different exposures, if your tornado speed V sub T is greater than some percentage of your basic wind speed. Now, as we'll see, we don't understand about surface roughness and exposure effects for tornadoes, but obviously it reduces your wind load. If you're in exposure B, you get 30% less wind load probably than you in exposure C, depending on the height of your building, right? And so this is a kind of how likely is tornado, again, to control over your wind speed. Well, if your tornado speed isn't greater than either half or 60% of your wind speed from B or C most of the time, then you can just stop right there. You don't have to do tornado. One of the key things that we put in the tornado load chapter is this really big user note, like a caution that kind of says, wait a minute, this is brand new, folks. You need to understand some things. We have some pointers to commentary. Importantly, let me highlight some key elements here. The tornado loads specified in this chapter provide reasonable consistency with the reliability delivered by chapters 26 and 27, a regular main wind loads. And therefore, they're only required for risk category 3 and 4 structure. The tornado loads are based on tornado speeds using the same return periods that we use right now. We have target reliabilities that are in chapter 1. And those target reliabilities for risk category 3 and 4, those are the same for tornado as they are for straight line wind. So when you're designing for this, your probability of failure over the life of the building, etc., you should have the same probability of failure for the risk category 3 and 4 as you have for failure for the regular one. So what that means is we're designing for the garden variety tornado, not the most intense. This work was done. It was a collaboration between NIST, Applied Research Associates, the ASCE 7 Load Combination Subcommittee, and the Wind Load Subcommittee. We adapted the reliability analysis that was used for the ASCE 716 maps to adapt for these new tornado load provisions. We conducted a series of risk-informed analyses to compare the proposed wind load criteria and the tornado load criteria. And our key finding was that tornado load criteria provide reasonable consistency with the reliability delivered in chapters 26 and 27. So bottom line here is, for risk category 1 and 2, at 300 and 700 years, the tornadoes are infrequent enough such that the tornado speeds that we would get are generally low enough that where tornado wouldn't control. By the time we get to 1700 and 3000 years for our risk category 3 to 4, those tornado very well likely can control, especially in this part of the country. And so we have those, and those are required, and we use the same return period. An important outcome of this is that the tornado speed at any geographic location will range from approximately EF0 to EF2 intensity, and that depends on the risk category and the effective plan area of the structure, as well as the geographic location. Options for protection for life and property for more intense tornadoes include storm shelter and or design for a longer return period or performance-based design. Again, we can design, we should design. Hopefully, like I said, you guys will advocate with your local codes and city councils, etc. Hey, let's adopt the 2024 building code. And if we haven't, if already amended out, don't amend out section 423 requiring storm shelters in schools, fire stations, police stations, and other emergency response. Okay. So tornado shelters, and one of the key warnings in this big commentary block is You can't design a tornado shelter based on, oh, we have a tornado load chapter, I can design a tornado shelter. No, they said the tornadoes that we're designing for are garden variety. Those are the common tornadoes that meet the current reliability. If you're, this is the map from ICC 500 that you have to design. You're designing for 250 miles per hour in this whole big area of the country here. You're designing for this 100-pound 2x4 instead of a 2x4, a 9-pound 2x4 at 34 miles per hour, etc. There's a whole raft of other requirements. You're going to design a tornado shelter, go to the ICC 500 standard. So our tornado load procedure that we're going to use, if you're familiar with the wind load procedure, it's very similar. We started with the tornado load procedure. We tried to keep things, everything from the terminology, the nomenclature, the overall procedure, and everything just about the same. Most of the things have been modified. Most of these variables are slightly different. But if you can do the wind load, you'll be familiar enough where you can pick up the tornado loads. We reference all the other the wind load chapters except chapter 28, right? That was kind of our envelope procedure that was commonly used by the metal buildings industry. The approach taken to develop the chapter 8 wind loads was incompatible with how we had data and available things for chapter 28. I will let you know that it's likely chapter 28 is going away in the next edition of ASCE 7. Chapter 27 will have major revisions. There's a $500,000 study that's recently wrapped up at Western Ontario to do much more wind tunnel testing of a much larger range of building shapes, and we'll just have one single method that's much more effective and reliable than having these two different methods of chapter 27 and 28 to get main wind force loads that can be very different between the two. Okay. In terms of our terminology, for example, if we have a gust effect factor that used to be G, we're going to give it a subscript with a capital T. So pretty much it's got a capital T on there at the end. That means it's a tornado version. There's a few little odd things like we already had a KDT for topographic features, so we made some slight adjustments there. But pretty much, we just pretty much added a subscript capital T, and that becomes a tornado. So our tornado velocity pressure, here's the differences from the equation that you're used to seeing. We have our Q, our velocity pressure, right? That's half, and by the way, it's not some magic, it's half rho v squared. Remember your fluid mechanics from undergraduate, half times the density times the velocity squared. The 0.00256 is just half rho in units conversion, so you can put stuff in miles per hour and get it out in PSF. And so instead of having a KZT, a topographic factor, times a KD, times the elevation, directionality factor, times the elevation factor, times the velocity, we have a tornado KZ factor, a KZ tor here. We've moved, actually, even for the straight line wind in ASCE 722, we got rid of the KD and we moved it to the pressure equation. Because KD wasn't really just only a function of the climatology. It has to do with the different building shape, right? You have a round building, you get a KD of 1, right? And you get different, so it has to do with the building as well as the wind climate. So that's got moved out. Elevation factor and a tornado. So it's a similar equation, but some things, parameters have been replaced. If we look about our tornado velocity pressure equation, remember I showed you the wind speeds are faster near the ground and they decrease aloft. So that's totally opposite from our exposure B and our exposure C, where we know that the wind speed increases with height above ground. If you like to sail, if you like to fly kites, all those things, that you got to get above the ground to get the higher wind speed. So our KZ and our KZ tor, we have a higher one, so it's a value of 1. So what that you can tell right there, if I got a low-rise building, only 1 story or 2 stories, I'm going to pay a price with that, and I'm going to have some higher loads because this KZ factor. But once I get to a medium or tall building, wow, the wind speed, the factor is so much less here. Tornado loads will not control tall building design. We've only seen maybe a dozen or so strikes of tornadoes over the years on tall buildings. It takes the cladding off, and it doesn't. We don't see significant damage. Those buildings are, and partly because the winds aloft are significantly reduced. The one part of tall building design that would be controlled by tornado is the cladding, particularly at the lower elevations, might be controlled. And if it's somehow an essential facility or the building is designed to be operational, then perhaps the cladding loads over the whole building. Well, the one thing is hey, that's easier, right? I don't have to worry about trying to figure out what exposure I'm in and get the aerial maps and look at that and there's exposure B or exposure C or something. Hey, it's just one exposure. It's one undefined exposure. And my building's less than 200 feet, which almost all buildings are. My KZ is just 1. That's easy. The next thing is I talked to you about the size of the building is really important. So how we define the size of the building is called not the plan area, not the footprint area, but the effective plan area, where we take a building. Here's a middle school near my house. I'm going to draw the smallest convex polygon that encloses the building of interest. Okay? And if I don't want to bother with that, I can just put a rectangle around it. It's not that sensitive to a small change like that, a 20 or 30% increase. It might be 1 or 2 miles per hour, et cetera. But that's going to be my effective plane area that I'm going to use for that building. And the reason is, if we think about it, let's just say this is a plan view of a U-shaped building. My tornado is not going to come around and do a little loop-de-loop and go back out here. If it goes over here, it's going to go over any different places. So any one of these different tornado tracks are all going to impact that building. But that's the same as if I draw this convex polygon around my U-shaped building. All those tornado tracks do the same thing, right? So the likelihood of the building getting hit is the same either way. So that's why we draw this convex polygon. And more importantly then, is what if I've got an essential facility and I've got the hospital here and the physical plant here? That hospital cannot operate without the physical plant, right? It's got the chilled water, it's got the cooling, it's got the medical gases, it has the backup generators, it's got all the stuff that's needed to run the hospital. And so you have to draw the smallest convex polygon around all the buildings that are relevant. You got the surgery center up here, then you're going to have to loop in the surgery center and bring that around, or again, you can just put a rectangle around it if you want. It's not super sensitive, it won't make that much. So how do you get what your tornado wind speeds are? I mean, there's paper maps in the ASCE 7 standard, but along with publication of ASCE 722, the hazard tool, just Google ASCE 7 hazard tool. That's free online. If you're not using it yet, oh boy, that's so easy. Say all your different loads. You want to get your ground motions, you want to get your ground snow load, all that kind of stuff. You just put in which version of ASCE 7 you want because it's free. It goes all the way back to ASCE 710. And you put in your geographic location, or you put a dot on the map, or you put in the coordinates, or you put in the street address. It'll put the location for you, and you can print out a whole report with all your hazards in it. For a tornado, so here for this particular location here, I got some place in Oklahoma, and we can see I've got a wind. It gives the wind right here. For a tornado, I've got a lot of rows here. It gives me a whole table here. I've picked, this case was a risk category 4 building, so I've got a column for 3,000 year return period. I've got all my different sizes from 1 square foot down to 4 million. And then I have these long return periods, 10 million, 100 million, 10,000, 100,000, a million, and 10 million. So if I'm doing an energy facility or a nuclear facility or something, I've got that. Back 10,000 years, some energy facilities use 10,000 years. DOT, LNG, other kind of things use 10,000. Use that. Our tornado load equations. Again, all the things that are in red are different from what you're used to dealing with. They're somewhat different. Not that different. So our pressure for our main wind force and for our components and cladding, our tornado pressure. We have our velocity pressure, QT. We're going to have our gust effect factor, GT. Again, we said we moved the directionality factor, KD, here into this equation. And then we also have a brand new factor called KVT, so it accounts for the differences in tornadoes and like the vertical updrafts and things. And then we also see the KD is moved out here for tornado because we don't have, for internal pressure, and we'll talk about that in a minute, internal pressure, the atmospheric pressure component, that's normally like, hey, I've got an open window, or et cetera, the wind's coming in, I get some opening effect, I get some internal pressure in the building, or even if I just have background leakage. And that is dependent on the wind direction, but atmospheric pressure change isn't. So since that's component, and that component can dominate sometimes, so that's why we don't get a directionality factor reduction on the internal pressure. So there's another difference, is we have a different KD, and the KD only applies to the external coefficient. It doesn't apply to the internal. Our KD value, I mean, for most buildings, we're just using 0.85 for wind. And like I said, there's a few odd things in there, like circular buildings and stuff like that, that have some numbers closer to 1, et cetera. Our KD for main wind force is 0.8. Again, we have these more rapidly changing directions, and sometimes the building is such that the building is smaller than the tornado. I mean, when the tornado is smaller than the building, then you get this less correlation and things like that. So we see a little bit less, of 0.8. And most of our components and cladding, it's only 0.75, except for in this roof, in the middle of the roof is our 1 prime zone. But one of the other things that we're different here is our KD factor is for components and cladding for essential facilities. We need to keep all the cladding on the building, not just lose a few pieces. We're going to keep the building operational. So our KD is 1 for essential facilities. We have debris considerations also for essential facilities. This is the hospital in Joplin. That's what it looks like inside. The buildings structurally are fine, all the buildings. So the 2 mid-rise hospital buildings, there's 4 medical office buildings with 3 or 4 stories. There's other smaller ancillary buildings. Little to no structural damage, a little bit of roof structural damage on some trusses on one or two of the buildings. Otherwise, the building looks like this, so on the inside. And here's a bunch of roof gravel. And thanks to folks here in Missouri, the Structural Engineers Association, that's not quite the exact, SECM, I think is the acronym, right? And some folks helped us with some pictures and some data from inside here when we wrote our Joplin report. And here's a whole bunch of the roof gravel off their own roof, breaking out a lot of their own glass. But the 5th floor, all this glass everywhere on this whole facility was gone, except for the 5th floor, which was the behavioral health unit. That was the psych ward. The psych ward had impact protected glass for patient safety reasons. And even in this horrible environment with huge debris flying around and everything else like that, that glass survived, right? And so we have requirements. If we build, we have the technology. I mean, could you have individual panes that break out due to a bigger piece? Sure. But in general, we can see we can survive with our current technology. So we have glazed opening requirements for buildings that are intended to remain operational. And realistically, if you're designing for tornado, you don't want your building to look like this, and et cetera. So you want your building that you're best off just to put in impact glazing. We do have atmospheric pressure change. Those of you who have even a little bit more gray hair than I do might remember even the Weather Service used to say, open the windows in your house to equalize the pressure so your house doesn't explode. Well, the house doesn't really explode due to atmospheric pressure change. There's this internal pressure, right? And we know the air gets in, and maybe you break a window, and maybe they get more internal pressure. But we already have plenty of leakage. We know we pay the electric bill or the heating bill. There's vents for makeup air and plumbing, and there's gaps underneath the door and around the windows and stuff. So there's opportunity for pressure to equalize. But as buildings particularly get larger and buildings get tighter with energy efficiency, APC does have a component. And so the way that it's not as simple as the way that we're doing it, but we've added the APC component to the internal pressure coefficient. And so we've made a couple of changes to our internal pressure coefficient. One, we've added a sealed other structures, and I've heard a few people already are taking this to think of a sealed building. This is not a sealed building, it's an other structure. This would only be applicable to stuff that you're designing, tanks and vessels and things like that, right? You can truly seal, right? You got a valve and it's closed and there is no equalization at all of the pressure. But for enclosed buildings, we have the high, and we have a positive plus 0.55 and a minus 0.18, instead of a plus partially enclosed of a plus 0.5 and a minus 0.55. And that's because if the building stays relatively sealed, when the low pressure of the tornado is over the building, then you have low pressure outside, but you still have what was the atmospheric pressure inside the building. And so those two can't equalize that quickly. And so you can have a contribution of the APC plus the positive internal pressure. We have this new modifier for KVT that accounts for the tornadic winds. And we'll see here that basically this accounts for the enhanced updraft on the uplift, which causes updrafts on the roof. We have negative or uplift pressure on the roofs. For main wind force, we got a 1.1, so we had 10% increase. And for components and cladding, depending upon which zone and which roof slope, anywhere from 5 to 30%. I will tell you, this was based on boundary layer wind tunnel tests where we changed the orientation of the buildings to artificially create some updrafts. In the tornado simulators, which from Texas Tech, from Missouri University of Science and Technology, right here in your state, from Western Ontario, University of Western Ontario, from multiple tornado simulators, we're seeing the same thing. That these updrafts, and ASCE 728, we're going to see probably some larger numbers here with this larger updraft. You saw it in the video, right? The winds come along, they suck that roof off, et cetera. And so we're going to see some larger numbers probably. At the moment, we don't have it. We just use one for downward acting pressures on the roof and for wall pressures. We also know we can have some higher concentrated wall pressures than we have in tornadoes. So you can expect to see these numbers going up as well in ASCE 728. Now, what are the impacts of these on wind load requirements? Well, gosh, is tornado going to control? It's a really hard question to answer because if we just pick, and I've overlaid here, this is for risk category 4. The black lines are the current ASCE 7 values. If we pick, say, a hospital or something with a pretty good size footprint, 1 million square feet, and the red lines are the risk category 4 tornado speeds, and we can see in your part of the country and where we are right here, our straight line wind speeds are going to be maybe 119, 118, 117, something like that. Over here, our tornado speed is going to be about a little bit more, maybe 120 or so, 120, 125, whatever. So that means tornado for sure is going to control a big risk category 4, almost all the wind load design. By the time, but it depends upon this area, it depends upon the height, it depends upon so many other different things. But tornado controls will control in a lot of cases. So we have kind of an example. We look at a junior high school here in St. Louis. What if it's an exposure C with risk category 3? If we had an effective square plan area of 250,000 square feet, hey, our basic wind speed, I can get it off the map here or go to the hazard stool, is going to be 114. My tornado speed, here's this map for 250K. That's going to be 93 miles per hour. Design for tornadoes is required because our tornado speed is greater than 0.6 times our basic wind speed. And it turns out with this difference, tornado is probably going to control the roof pressures. It might control the leeward wall, etc. What happens is the walls, the elements of the building that are more sensitive to change in internal pressure, like the base shear doesn't matter. Internal pressure goes up or down. If I'm designing a foundation for base shear, it doesn't matter. Those two things cancel out. But if I'm designing just the leeward wall or just this individual walls, whatever, then those are going to be more sensitive to the APC change, etc. So with this difference of like 20 some odd miles per hour, tornado will control some but not all of the wind speeds or the pressures. And it gets kind of complicated here. If we've got this hospital in suburban St. Louis, and let's say that's exposure B, now my basic wind speed is going to be 119. My tornado speed is 121. For sure, tornado is going to control most of your wind load. But to get really specific about which element, because you have to look at every different beam, at your different cladding systems, components, all that kind of stuff. So here's an example. If we look at the main wind force design of the windward wall, and what I'm plotting here is a ratio of the tornado pressure divided by the wind pressure. And let's just assuming that the building is an exposure B, and I have to have a lot of variables to be able to do this calculation. This, I'm assuming a 2-story elementary school that was risk category 3, that was 100,000 square foot, and I'm comparing these design for the main wind force. And if these dashed lines over here means I don't even have to think about tornado because I'm west of the Rockies. And the black is, hey, my speed is less than 60, so I wouldn't have to design this elementary school in the first place. And the gray area is, you know what? It's not less than 60. I might have to design it, but it turned out that I calculated my tornado load and I calculated the main wind force pressure on the windward wall, but tornado didn't control in the gray area. And if I'm in the white to red, tornado did control. And here, depending upon the darkest color red here in the middle is about 1.45. That means tornado load controlled the windward load design up to about 45% in sort of the middle of the country here. So is tornado going to control? It's a very specific, not only to the building, the size, the location, but which component of the building you're dealing with. Because we have these different uplift factors, and we got the different change in atmospheric pressure, it's not like you just take, here's my wind load design and multiply it by some ratio and get a different set of pressures. The pattern of the pressures is different, right? You have a different shape, and it's not all just the same. Some go up higher, some relatively faster than others. If we look at the leeward roof uplifts, or if we're getting kind of in the back side of the roof right here for the same elementary school, we see it's going to control in the larger part of the country, and here the ratio is about double the uplift on the leeward side of the roof. If we take a hospital, here's a 1 million square foot 5-story hospital, risk category 4. Just looking at here, design, we're in the field of the roof someplace, in the building's exposure C, or exposure B, I'm sorry. Tornado is going to control uplift on that roof in most locations. So where are tornado loads likely to control? They're more likely to control if at least some element of building design, if your building is located in the central or southeast U.S., like you are here, except for if you're near the coast where wind speeds are dominated by hurricanes. Risk category 4, because the tornado speeds increase more quickly with higher return periods than the straight line. If you have an essential facility, I said we have a few different provisions that increase the loads for essential facilities. The bigger your effective plan area, you're more likely tornado control. You're more likely for tornado control over wind if you're in exposure B, not because your tornado loads change, but your wind loads go down. So if your wind loads go down, then relatively tornado loads are more likely to control. Because of this difference between wind speed increasing with height for straight line winds versus wind speeds decreasing with height for tornado, buildings that have a lower mean roof heights are more likely to have tornadoes control. And if you started out classified as enclosed building to begin with, then you have to go to that plus 0.55 for the internal pressure in this location. So bottom line here is where tornado loads control, design uplift pressures, especially on the roof, will increase. Now the good news is that's going to also increase common failures from other windstorms. Where's our first failure start? Our failures typically start roof cladding, roof covering, roof attachment. et cetera, right, in addition to window breakage and some lightweight siding failure. So moving tornado loads into practice, we're successful in getting the tornado loads incorporated into the 2024 International Building Code, also into the NFPA 5000, which is hardly used very much here in the US, but we've got that. And what it just says here, design and construction of risk category 3 and 4 buildings and other structures that are located in the tornado-prone region, as shown here below, shall be in accordance with Chapter 32 of ASCE 7. There's a few other bits and pieces here where they had some simplified wind thing. We said you can't do tornado with that, et cetera. But basically, IBC says go see ASCE 7. This is a free download for you. I should have put a QR code, but if you just Google NIST FEMA Tornado Design Guide or something like that, that'll pull you up as a 32-page design guide that includes example calculations. And it has some kind of more expansion of some of these topics that I talked about today. We've got sort of a typical hospital. It's got some examples in here, so I just encourage you to Google that. Just Google, get FEMA NIST Design Guide for tornadoes. So let's kind of wrap up here. What did we talk about today? Tornado load requirements and our impacts. Our risk category, they're going to apply our tornado load requirements to apply to risk category 3 and 4 buildings in the tornado-prone region. That's going to be our assembly, occupancy, schools, nursing homes, fire, police, EMS. The speeds that we're designing for in these maps are going to be about EF0 through EF2 speeds, like 60 to 138 or something is the range of maps that are in our standard. And so that depends on your location, your risk category, your plan size. We're designing for the most common tornadoes, not the most intense. We're designing the reliability that we use is the same reliability that we're using for the straight line winds. If you want to design for the most intense, put in a storm shelter. Right? Go to ICC, Google ICC 500. You can get a basic version for free. Right? You can't print it or download it, but you can at least view it online. Now, in some cases, particularly for larger facilities, our loads can increase significantly, sometimes greater than 100%. Maybe we double the uplift on the roof. We did a study. We worked with our NIST Office of Applied Economics. We worked with some designers and school designers in Dallas, a roofing expert, Tom Smith from Chicago. And we went through and chased these through for an elementary school example and for a high school example at 9 different cities. We didn't include St. Louis. We had Kansas City. We had Memphis in here, et cetera. You can look at the details of those. And you know what? Even if your roof load increases a lot in some places, maybe it's a 0.1% increase in the total construction cost at the most in some of the cities in the center part of the country. Because even your roof cladding, you know what, the roof cladding systems, they have these different classes, and maybe you go from here to here, but you might go up 20-30% increase, so it doesn't even change the roof class of material. You don't necessarily have to do it. What it typically did is maybe in some cases you need the next thicker roof deck size, maybe you need more connections from your clap and fasteners, maybe you need to beef up to the next bigger joist size, et cetera. But the changes are pretty modest overall to the overall structure. So what comes next? Some current and future work that we're doing at NIST, R&D, research to support improved tornado climatology and wind structure interaction, working to update the tornado load methodology we use in 728, support for local adoption of tornado-resistant codes. So I'm here today for supporting you guys here in understanding. Guidance for cost-effective strategies for tornado damage reduction, including risk category 2. We've got a focus on warehouses. We have a report in collaboration with ASCE that will be published by ASCE soon about a FedEx warehouse collapse last year. And this will be publishing it's our own report later this year on studying 3 different warehouse failures. Improved guidance for identification of best available tornado refuge areas and guidance for public tornado shelter strategies. Working a lot with my alma mater, Texas Tech University. They have the largest tornado simulator in the U.S. Play this video right here. So here's the tornado simulator. They have a moving ground plane. Here's a model of this building, which is actually a full-scale wind lab. We've done boundary layer tests on that same model. We put that model in the tornado simulator. So we have some much better apples-to-apples comparison of what the tornado loads are in the building versus what the wind loads are in the building. That will be bringing some exciting work. This is also another free report we just published with ASCE. A state-of-the-art report on research needs and tornado design. Alex also was a co-author on that, as well as myself. So just Google state-of-the-art report from ASCE on tornadoes. So we document what's the state-of-the-art on all aspects of tornado design and identify key research needs. And with that, just go ahead and wrap up and answer any questions. I threw a lot of information at you, kind of a whirlwind of information, but one of the guys, yeah. And here in the back. Sure.
What is on that area? So it makes total sense. You're trying to do like hospital here, up there, that type of area. Like what happens? Still in a full. How do you consider that? Not like an earthquake, tornado. Plant is 20, so you design for 100. That's where what is the right approach in building right?
Yeah, and I will say as Marc Levitan, not as NIST, not as ASCE, this is my own friendly advice, whatever. I would just assume, I would just use the same rules and assume what it is, because other buildings will get replaced or whatever, and that'll be your best point in time to give the best performance. It's not like, if it doubles or triples, then you add 5 miles per hour or 10 miles per hour. If you go from, oh, this little building I'm adding is only 10,000 square feet, but now I got to consider it as 1 million square feet, then you're talking, 20 miles per hour maybe or something. But, that's not peak. But overall, like I said, the costs are not that much, even in the cases where the pressures are going up. But it gets you better protection. So I would just suggest use the current definition, whether or not.
Question. Probability, liability. Then the client asks, oh, there are stronger tornadoes. What do you tell the client? No good enough for greater windstorm.
Yeah, because the reliability basis is just for the wind loads on the main wind force system that does not include debris consideration. Actually, it doesn't even include components and cladding. Right? Components and cladding is not designed on a reliability basis right now. It's the same wind speed, and we do that. There are no separate reliability calculations, no requirements in ASCE 7 for reliability. So yes, you would still want, because it can be more intense, or you could have bigger debris than we designed for. Right? So it could be more intense. So you do want to think about that and move your patients out in hallways or other areas. But as we saw, you're just far more likely to have your glazing survive, and the building just won't be completely blown through with the furniture on the ground outside. You got the impact glazing in there. Now, I will also say, you saw in that video how that was a EF3 tornado, and we can have much more larger debris, individual debris, etc. But a lot of it is smaller stuff. We made the decision to use the same requirements we use in the hurricane-prone region, which is a much smaller, just because there's lots of products out there, right? And this is important, as you start to talk to your suppliers, right? The tests that they use are the hurricane test, which includes this 9-pound 2x4 at 34 miles per hour. But they also require cyclic testing. Our tests don't require cyclic testing, so any product that meets the cyclic test for the hurricane, because the hurricane's got to last hours, right? It's got to hit by the debris, it's still got to keep the water out, etc., over the next hour, or 2 or 3 or 5 of the hurricane. There's an opportunity there in the industry, if you're in the glazing industry, for you to make products that are specific to tornado, and maybe there's some cost savings there, right? Because you don't have to make it where it can withstand, it just has to withstand the static pressure. It doesn't have to withstand all these cycles. It has to withstand the impact, it has to withstand the static pressure. It doesn't have to withstand the cycle. So as we're really hoping right now, you talk to folks in the glazing industry, it's something like impact glazing is something like double the cost, ballparkish, right? To get the correct glazing. But because of that requirement, we don't require the cycling. As we start to get a lot more adoption of ASCE 722 tornado load requirements, maybe there's market share there, and companies that can develop a product, you know what, I don't need quite as much, I don't have to have that stuff right there, maybe the cost will come down, right? And there'll just be so much more need for impact resistant glass than just the hurricane codes, right? So maybe economies of scale, get more manufacturers. Really hoping that the impact requirements come down. Having said all that, we just don't know all that much about debris. We need a lot more research in there. I don't know that we're going to have huge changes in our ASCE 728 in that area. That's an area that we need to do a lot more.
Any other questions? All right. What do you think? Did he blow you away? Thank you, Dr. Levitan. Will you do me a favor and pick our winner today?
from Washington University in St. Louis, Jared Marc Levitan. Did I pronounce that right?
All right, come on up.
There we
Thank
go.
you folks so much for everything today. We hope to see you next week for our final seminar of the season. If you got any questions,
I'll stick around for a little while if anybody has questions.
this is for you.
All right.
It's a really handy guide. Yep, appreciate you.
Oh, thank you.